To start a fusion reactor, you don't flip a switch and watch the lights come on. To even initiate the reaction, the facility must begin by absorbing a massive surge of electricity from the local grid. Before a commercial reactor produces a single net watt of electricity, it operates as one of the largest parasitic loads in the energy system. Fundamental operations require continuous, heavy pulsed power. You need staggering amounts of electricity just to maintain the vacuum and fire the heating arrays that spark the plasma. Then there are the superconducting magnetic containment fields. Energizing these coils creates an extreme inductive load that must be carefully managed to prevent a grid collapse. This reality is often lost in the focus on Q-psi, or scientific breakeven. That metric only measures whether the plasma itself produces more energy than it directly absorbs from the heating beams. The true operational hurdle is Qeng, engineering breakeven. This accounts for the massive recirculating power required to run the entire facility's electronics and support systems. Delivering a commercial reactor requires integrating these physics breakthroughs into a systems architecture capable of managing megawatt-scale parasitic loads. Solving the engineering breakeven challenge requires analyzing the reactor as a complex electrical schematic. The primary circuit consists of the grid input, the massive inductive magnet coils, the heating arrays, and the high-speed sensor networks. Conceptually, the superheated plasma acts as an unstable, variable resistance secondary coil inside a massive transformer. The primary engineering tension is keeping this secondary coil energized and confined, without triggering electrical faults that cascade through the rest of the plant. Confining a 100 million degree fluid requires balancing extreme electrical forces. A single misstep can melt the reactor's own circuitry. To meet the Lawson criterion for sustained fusion, tomacs rely on immense magnetic fields to cage the charged plasma particles. Utilizing traditional low-temperature superconducting magnets requires an incredibly massive physical volume to achieve the fields necessary for confinement. High-temperature superconducting tape, specifically REBCO, has changed those constraints. It can generate magnetic fields exceeding 20 Tesla. This comparison illustrates the volumetric reduction made possible by REBCO tape. The physical footprint shrinks from the massive ITER cube to the compact spark and arc designs. Shrinking the core volume reduces material requirements and upfront capital costs. While HTS solves the volume problem, the extreme field density creates a severe energy storage hazard within the coils themselves. During operation, these compact HTS magnets store immense amounts of localized electromagnetic energy. The risk is a quench. This occurs when a microscopic section of the REBCO tape drops out of its superconducting state and suddenly exhibits electrical resistance. When that resistance hits, the stored magnetic energy has nowhere to go. Physics forces it to convert directly into extreme thermal energy. If that runaway heat generation is not bypassed instantly, it will melt the magnet coil and destroy the surrounding containment structure. To prevent the coil from consuming itself, the power electronics must feature ultra-fast quench detection systems that monitor the coils for micro-ohm resistance changes. The moment a quench is detected, heavy-duty energy dump circuits must instantly route stored power out of the failing coil and into external resistor banks. Managing these quench risks makes compact fusion a high-stakes, ultra-low-latency electrical protection problem. Inside the vacuum vessel, the challenge shifts to the plasma itself, a highly turbulent, electrically conductive fluid that actively resists magnetic containment, generating severe instabilities. The most fatal disruption to the reaction is the tearing mode instability. During a tearing mode, the magnetic field lines actually snap and reconnect. This creates isolated magnetic islands within the plasma flow. These islands act as thermal leaks. They bleed heat out of the core and trigger a full reactor disruption. Traditional PID closed-loop controllers are too slow to react to these rapidly evolving, nonlinear plasma dynamics. Static physical containment cannot hold a burning plasma. It demands an active, highly predictive control architecture. A solution was recently demonstrated at the D3D facility, deploying deep reinforcement learning as an active feedback controller. The controller ingests massive arrays of real-time diagnostic data and telemetry from hundreds of plasma sensors. The AI then forecasts the formation of a tearing mode instability up to 300 milliseconds before it physically manifests. In that 300 millisecond window, the model instantaneously maps a stable path through the operational space to avoid the instability threshold. The AI then actively modulates neutral beam power and magnetic coil geometry to alter the plasma shape. This dynamic loop successfully steers the high-pressure plasma away from disruption, smoothly maintaining stability without terminating the ongoing fusion burn. Artificial intelligence has transformed plasma containment from a reactive physical barrier into a proactive high-speed software control loop. Perfect AI confinement and stable HTS magnets are only part of the solution. A deuterium-tritium reaction does not output electrical current directly. The actual physical output of the reaction is a massive surge of kinetic energy carried by uncharged 14.1 MeV neutrons. Because these neutrons have no charge, they bypass the magnetic confinement cage and strike the reactor's outer wall, known as the lithium blanket. This impact breeds fresh tritium to sustain the fuel cycle while generating intense structural heat. This heat is transferred out via a coolant loop, shifting the physics challenge back into a conventional thermodynamics problem. The coolant loop drives a standard steam turbine, finally crossing the Qeng threshold to deliver net zero carbon electricity to the grid. Delivering commercial fusion relies on solving the rigorous electrical engineering challenges of pulsed power, quench protection, and AI-driven control architectures.